Morning, everyone. I'm Sahil Chawla. I'm currently employed with UMTC, Urban Mass Transit Company. I'm an architect planner. Okay, so we'll start with the topic effectiveness of the queue jumper lane and transit signal priority for the bus performance improvement. This can be a smart traffic solution for the smart cities, as most of the Indian cities are having bus as a major transit mode. So the presentation structure is as follows: the introduction followed by aim, objectives, then study approach, literature review of the same, then model development, that is micro simulation model in Vism, result evaluation and conclusions. So we start with the introduction. So what are queue jumpers basically? These are the bus priority systems which can be used as a smart solution for the smart cities. Then we have various examples like King George Boulevard at 96th Avenue, the bus queue jumper lanes provided at the junctions. Why we need to have this, or what is the purpose of this research? Like, we have poor policy and institutional framework in India, then limited financing and resources, deteriorating environmental quality, fuel consumption. So we just can't go with the metro in all of the cities. We have to augment the existing bus systems in Indian cities. So the bottom approach, that is significant improvement in the bus services and operations basically, can serve as a smart transit mode in the upcoming smart cities having low ridership or low demand. So the need for research, these are various Indian city profiles. We can see the share of bus to the total vehicles and buses to the million population increasing from 237 to 1325 buses to million population, that is huge. Then average trip length is for category 1 cities, that is 2.4, and category 2, that is having population of 5 to 10 lakhs, average trip length is 3.5. So these are the, from category 1, 2, 3, these are the cities using bus as a major transit mode. So the study aims at the assessment of the effectiveness of the queue jumper lane and signal priority on the bus performance. Research objectives are performance objective, assessment of the queue jumper and TSP, and second, using micro simulation model tool for bus performance improvement. So research approach is as follows: the review of literature and regulatory design, followed by primary and secondary data collection for model development, then scenarios generation and evaluation, followed by the calibration and validation of the model, then conclusions. So literature review, like for various bus priority system, we can observe, like for dedicated lane based system, improved level of service, travel time saving. So this queue jumper is also a kind of dedicated lane based system at a junction only if we are having space constraints. Then the scale of projects can be strategic at a city-wide level, then mesoscopic, that can be a grid of streets, and microscopic, that can be few junctions. I have taken various evaluation parameters like travel time variability, delay, headway variability, and incidence of the variability. Like various authors have done assessment of the queue jumpers. The first one, they have assessed like how different signal priority strategies, fleet size, volume, detector locations just before the junctions, then dwell times and bus stop locations. Then the second one, they have simulated the 13 intersection and transit travel time. They have observed the reduction of 13 to 22%. Then in 2013, they have modeled 6 signalized junctions, and reduction in delay was observed by 30% along the corridor. So next is the model development. The first one is the test corridor, which is from the Shiv Ranjani split flyover to the APMC road junction in Ahmedabad, that is a part of 132 feet ring road. Number of lanes are 4 on each side. Currently no segregated bus lane is provided. The land use is predominantly mixed use, and there is a proposed prioritized bus plan that can be a BRTS or BRTS augmented with signal priority, and this will serve a feeder to the proposed metro that is coming over here from APMC road junction to the Jivraj Park, then metros goes over there. So total junctions are 8 and signalized one are the 4. That is the first one, Premji Nanji Crossroads. Then we have Shamal, Jivraj Park, and APMC road junction. So the Vism model development involved pre-modeling work that included data collection, followed by model preparation that included network creation of network elements, origin and turning volumes at the mid blocks and junctions, then traffic composition and defining the vehicle types, defining parking areas and duration, signal phasing programming, and inputs to the driving behavior that are Indian. Followed by the basic model development, we have multiple simulation runs to obtain speed-based results and volume-based results. So we have multi-criterion approach to for the calibration of the same. And same was if you compare that with the field results, and that is within the confidence limit of more than 95%, then we have a calibrated model and we can generate the scenarios. And this model can be used for various applications. So the calibration process involved various trials with the Wideband 99 parameters. First, we have taken the default parameters and all those default values for the standstill distance, headway time, follow variation of the vehicles, general behavior that shows lane rule, desired position at the middle of the lane, and then lateral distances that is unticked, and for various desired speed distribution, default values were taken. But the results we can observe in the validation process. The trial second onwards included the modification of look ahead distance, look back distance basically, and the standstill distance was reduced to 0.2 to 0.9. The values were varying, various iterations having different values. Then the headway time was varied, follow variation was varied. The general behavior was not the simply the show lane rule. It included show lane rule or simply free lane selection, and desired position as observed in Indian condition would be middle or any. Then desired speed distribution varied iteratively, and maximum being the free flow speed at the low volumes. Then trial 7, for this we found the calibrated model, validated model having a confidence limit of 95% or more. The value for look ahead distance and look back distance was 20. The standstill distance was 0.2, headway time 0.9, follow variation 2. General behavior was free lane selection, and desired position at free flow was any position at in the lanes. The desired speed distribution, lower bound and upper bound values were as follows. So the first criterion was the volume and Q lengths at the junctions. So we observed the field, we have the field results and the model outputs, and we observed the percentage error. So these are the Q lengths we have calculated out of the model, and these are the field result, and percentage error can be seen. So the roads or the links along the corridor, those were having a percentage error of less than values less than 10. The second criterion was the travel time and delay. That was link wise, because this corridor has a comprehensive kind of structure, like a free flowing speed from the highway following till the Jivraj Park crossroads. Then we have an elevated section also. Then we have a wide section from Jivraj cross junction to the APMC. So we have to validate the results of travel time and delay link wise. So we have the field results of the travel time and model. So the residual error, the maximum can be seen as the -11. So that was within the confidence limit. So based on that, we have a calibrated and validated model. We developed the scenarios. We have a base scenarios which represent the base network, curbside bus stations, and no signal priority is given currently. Then we have a queue jumper, and queue jumper will only be effective if we are having a active signal priority. Otherwise, if bus can't maneuver through the traffic, it can't get a signal priority, and this queue jumper won't be effective. So we have, in this case, we have a queue jumper at the junctions and curbside bus stations. Curb extensions are provided over here. So curb extensions is another bus priority measure taken, so that the time taken by maneuvering till the last lane is reduced. And signal priority given over here is vehicle actuated signal priority. Detector detects the bus just approaching the junction, and it provides the green signal to that. So we have compared the results. We have seen like for BAU, we have taken the value 0. The travel time reduces by 15.5%, and that was resultant of the reduction in bus delay. The bus delay was decreased by the 27%. So we concluded VAP, that is active priority, resulted in maximum delay reduction. And secondly, vehicle maneuvering from one lane to another resulted in delay. That was very less amount. And if we provide the passive signal priority, that can only work if the traffic is quite high, V by C more than 0.8, and bus is taking more than 2 cycles to cross the junction. That is only effective. Otherwise, VAP, that is vehicle actuated priority, shows maximum improvement. Then we have the travel time variability of the various vehicles for the time we have run the simulation. We can see the variation of minus 88 seconds to 158 seconds. That is huge. That is plus minus 30% of the variation from the scheduled timing. Whereas in case of queue jumper and vehicle actuated priority, the variation is quite less, 0.5 to plus 10 variation. That is just 19 to 28 seconds. This we can, across the corridor, we can see how the vehicle is behaving or where it is getting the maximum. Like in first case, this is the red one shows the junction. So this is Shamal Crossroads. It shows the large variation in junction delay. Like in this case, we have no delay. It got green in just, and here it has got full cycle, full red cycle over here. Then this gap basically is the deviation from the scheduled headway. So at the end, we can see there is large variability in case of business as usual, and there are maintained headway in case of queue jumper and signal priority. The headway variability across various stations can be observed. These are various bus stations. There is large variation, and the vehicle are actually following, and at the junctions bus bunching would be happening, whereas in this case there is uniformity in case of, and there is hardly any variation, plus minus 2 seconds in case of this one. So headway variability is greatly reduced. Then we assess the impact of increase in traffic, whether the queue jumper is effective in case of increasing the traffic for V by C more than 1 and so. So for increase of 5%, 10, 15 up to 50, we have observed there is an exponential increase in the queue length. And because every time the bus is getting green, if we are increasing the bus frequency also, we are getting huge queue lengths of the private vehicles over there, and it surpasses the queue jumper lanes length. So the bus can't even get into that queue jumper lane. So this solution can be a short-term solution or can be a solution to the feeder system that is running at the periphery, or some kind of feeder to the mass transit system. So the queue length comprehends over the previous junction also, like in this case we can see. So bus cannot cross this junction and this one, so the delay for the bus also increases exponentially. So we can conclude queue jumper lanes have to be provided with active signal priority, and in short term the results are comparable to the buses running in the segregated lane, that is BRT, provided with any kind of signal priority. Then in long term, the delay and travel time increases exponentially, both for bus as well as private vehicles. There are worse impacts on the private vehicles itself, and overall there is poor network performance. Thank you.